Hello everyone, and today we are going to uh, go over some of the basic terminologies that are being used repeatedly in our course Linear Algebra, and some of the students um, asked to go over these in a bit detailed manner so that we can continue with our understanding of linear subspaces. Um, So we will go over these three specific terminologies. The first one we will be talking about is called linear combination. Then we will move into span and basis. So in order to formally represent what we mean by linear combination is that let us say that we have vectors v1. I'm putting an arrow on top of it to make it a vector. Then we have another vector v2, okay, and so on with three dots, and then we reach to a nth vector. So all these vectors are in an n-dimensional space, a real space, okay. So each of these vectors contains n components. So this is an n component vector. This one is also an n component vector, and n is also an n component vector. All these vectors v1, v2 up till vn belongs to n dimensional vectors. Then what we can do is we can add these vectors. So I'm going to add these vectors now. v1 plus I have vector v2, then plus I will have v3, and till I will reach this addition will reach till the last vector, which is vn. So I am going to add those vectors, but before I add them, I can pick some arbitrary constants. So let me pick those constants. So here is the first constant, which is C1. Here, this C1 is a constant or a scalar that is multiplied with this vector. Then I can pick another constant, C2, and multiply it. So here is C2, multiply it. Similarly, I can have a vector, a scalar Cn multiplied with the last vector Vn. So here is now a scalar multiple of each vector. So if you look into this combination as a whole, so let me illustrate this particular terminology. This is a scalar multiple of a vector. When you do a scalar multiple of a vector, what you are doing is you are not changing the direction as such, but you are scaling it up and down. So this is a scaled version of the vector v1. So I can say it scaled version of vector v1. So this whole idea is that you are scaling it up and down. Similarly, when you go for C2, V2, you also are doing scaling, but now you have this plus. This plus represents a vector addition. So I will say this plus is not an ordinary addition. It is a vector addition. And you know that vector addition is done component wise. So this is a vector addition. Okay. So if you do all this, you take a scalar multiple of v1, then you add it to a scalar multiple of v2, and then you keep adding on until you reach to the nth vector, and then you scale nth vector and you add it. So you got, once you add this, you will get a resultant vector. So let's represent our resultant vector with the green, okay, color. So this is, let's say I reach to a vector x. Now this vector x is the resultant of all that operation that we did. And this whole operation where we do the scalar multiple of a vector and then we add a bunch of vectors together and we end up with the resultant vector x. But keep in mind this x is also a member of the same space from which these vectors came. So it's also belong to nth dimensional real space. This whole combination that we did, we scalar multiply and then add, this is called linear combination. So this is a linear combination. So what we did is a linear combination, and a vector x is generated as an output of that linear combination that we just employed right now. Okay, so for the sake of discussion, we will go for something that we can understand and we can graph it more conveniently. So let's look into a Cartesian coordinate system that is a very good representation of two-dimensional real space. So let's look into two-dimensional real space. For this, I will just clean up my formal definition right now. So here is, I'm taking care of the cleaning operation here. Okay, and then I will move on to, yes. So now I will go for a very specific example. So let's take up this R square. So consider R square, a two-dimensional vector space, which can be easily represented by a Cartesian coordinate system. So right now here in front of us in this graph, this is an R square. So this is like a Cartesian plane in which we have an x-axis and we have a y-axis. Okay, so let's pick two vectors here. Both belongs to R square. So one is A, and let's pick A as 2, 1. Okay, and let's pick B. B also belongs to R square, and it is what we call them 0. This is 0 and 3. Okay, so if you pick these two vectors A and B, I can graph them on this Cartesian plane because R square. So I will just pick. So let me give you different colors. I think it's better. Let's depict this guy as a red color. Okay, so here is B, and I can write it as 0, 3. And I can do this A as a green color, so that we are in a color coding scheme right now. So just to give you a discrimination, a nice discrimination. Okay, so now we have a green color A, which consists of two components, 2 and 1. It belongs to R square. Okay, and B is also a vector which belongs to R square, and it has components 0, 3. Now one thing is you can see from the choice of the vector that I made, I made sure that A is not a scalar multiple of B. Okay, so this is not. This is the only care I made while I was choosing AB, and I will tell you why I made this care. But anyway, let's draw them here. So here is, you go along this 2 units, and then you go up 1 unit and you reach to this point. Okay, and now you basically take this arrow and put it right here. Okay. So I will do it like this. Okay, so this is my A. Okay, this is my A vector, and now I wanted to depict the B. Okay, 0, 3. So 0 along x-axis and 3 along y-axis. So I should reach here, and I'm going to do this Okay, so this is my B. Okay, now you can see that A and B are not in the same direction as I said here. You see, this fact, which I'm saying A is not a scalar multiple of B, this is depicted right here because they both are not in the same direction. Now I can do a linear combination of these two. So let me pick a linear combination, 0 times A plus 0 times B. If I do this, I will end up into a 0 vector. Now keep here in mind that this is a 0 vector, whereas these two are 0 scalars. So these are numbers and this is a vector. So this 0 actually represents 0 and 0, two components. So I'm right at the center. Okay, I will just do the resultant with different color. Let's say I pick a color, gray color, and now I'm going to do this. I'll pick another color because I'm not able to see it. Let me pick a blue color here. Okay, so if I pick a blue color, I can see very clearly here that so here is I will pick now 3A minus 2B. Now this is also a linear combination and I want to graph it. Now 3A means I will take A, I will further extend it 3 times. This is 2 times, this is 3 times. So now this is 3A. Starting from the tip till this is our 3A. Okay. And now we are going for minus 2B. So B is this. So I will go minus, this is minus B. Then I have to do, oh my God, I'm coming out of it. Okay. So let me take the liberty here. So this is this whole arrangement from here till here. So I will say that this is minus 2B. Okay. And now I'm going to combine them. So if I'm going to combine them, let me take the green color. Okay. I will go straight down and then I will go up. Okay, like this. And I will come straight down and I will meet right here. And this is my resultant. Okay, this resultant is 3A minus 2B using head to tail rule or parallelogram rule, whatever you feel more comfortable with. Okay, okay, so now this 3A minus 2B, we reach to this point. Okay, similarly, if I want to reach to any other point, let's say this point, then I can do this. And how I'm going to do this, it is very interesting. Here, I will pick my B and I will pick my A. So my A will go backward from here. And here it goes. This is backward. Since I want to reach to this point, okay, so I will take my, I will reach here and then I will go up and I will do this. So this is my A that I need, and this is my B, and I will reach here. So any point you give me on this particular two-dimensional space, this Cartesian coordinate plane, and I should be able to reach it fairly easy by using my A's and B's. So let me give you a general idea of about all the linear combinations associated with A and B. So let me clean it a little bit, this graph, and then probably, okay. Now I can clean this a little bit. Okay, and I can, okay, I will go back to A and B. So I just have those A's and B's. And now I'm looking at, right now my aim is to look at, now my aim is all linear combinations combo. Okay, this is kind of like C1 times A, which is 2, 1, plus C2 times 0, 3, where C1 and C2 are arbitrary constants. So I'm using arbitrary constants and I'm taking the linear combination for A and B. And I want to see how much area I can cover, how much points are there in R square that I can reach. Okay. So now let's look at this very clearly. So now let's say my A is this one and my B is something that I can reach up and down here. So I can cover this whole line. Now I can increase my A a little bit and then I can cover also this line. Now if I increase it a little bit more, I can cover this other line. Similarly, if I go backward A, I will cover this line. Then I can do this and so pretty much if you do this whole exercise, you can convince yourself that by playing an appropriate values, scalar multiple of A's and B's, you can pretty much cover everything that is in R square. So we can say that if you take all linear combinations where C1 and C2 are any arbitrary constants belonging to the real line, then this linear combination will reach up to every single point on R square. So saying this big notion, we can go to the next concept, which is span. So what I'm saying right now here is that the span of A and B. Now, when we say span of A and B, now this is our second concept. So the span of A comma B. When I say this span of A, what I basically means from this is that I have C1 times A plus C2 times B, where I'm saying that C1 and C2 both belong to real line. So I'm looking at all combinations, all linear combinations where C1 and C2 are kind of like free to choose any values from the real line, where A and B are fixed. That's why I'm saying span A and B. A and B vectors are fixed, but C1 and C2 could be any arbitrary constant. If I do this, I will basically reach and make the whole, I will reconstruct the whole R square space. So the span of AB will reach up to covering the whole of R square. That's really amazing. So in other words, if you choose two vectors A and B, and these both are linearly independent. Now I will just go over it. What is linear independence? So let me clean it a little bit more so that I can have the space. Now, what I'm saying is, if I have two vectors and they are linearly independent. So here, if we got two vectors in R square, if we got two vectors in R square, okay, and this is an R square real space, then their span, let's say these two vectors are A and B, it will be equal to R, provided, now there is a very big condition attached to it, provided A and B are, I will just emphasize it with a different color, are linearly independent. So if this A and B are linearly independent, then they will span whole of R square. So when we say linearly independent, what we mean is that, so let me explain this. What we mean by this is that none of the vector is made from a linear combination of other vectors. So if I just clean this up and just say, okay, so here is, so A and B are, so A cannot be made from B by using any scalar multiple. Okay, so let's assume that we change our A and B. So our A is now the same 2, 1, but our B is now 3 times 2, so which is 6. 3 times 1 is 3. So let's say my B is 6, 3. So now if my B is 6, 3, so what will happen to my B? So let me pick the red color and show you this B, this new B. So my B is now no longer this B, but my B is this one. So here is A and B is like 3 times this. So here is, I will start my B that will go here. So this is my new B now. Okay. Now you can see very clearly that A and B are in parallel. And B can be made from A and A can be made from B. So these are not linearly independent. So if I take the linear combination of this, so let me take the black color. So if I make a linear combination of this, I can make all the vectors. So I'm here one vector, I can make this vector, I can make this one, I can make another this one, this one. So I can reach up to all the people on this line. So the linear combination of A and B will end up with all the points which lie on this line. Okay. So this line is reachable by linear combination of this A and B. So if I say span of 2, 1, comma 6, 3, then I will say a line. So the span of this is a line. This is not R square. Whereas the span of the previous one, where A and B were linearly independent, it was the complete R square. But in this case, the span is not the whole R square. Rather, the span is just a line. For example, let's say I pick a green vector here. This is my C vector. Can I reach up to C? No. By using this A and B, the one that I just defined, which are linearly dependent A and B, I cannot reach to C. So saying that with this particular combination of A and B, I will have certainly some vectors that are not reachable. So the space that is covered by A and B, that the linear subspace that is covered by this spatial A and B, in which A and B are parallel to each other, will be just a line. Okay. But if A and B are not on the same line, then they have the capacity and the potential to fill the whole R square space. Okay. Now we are good enough to go for proving this fact that if your A and B are not on the same line, then we can basically fill the whole space. Okay. I will just clean this thing here. Oh. Now the same thing as we did last time. So let us say our A is 2, 1 and our B is 0, 3. Okay, so these are not linearly dependent, rather they're linearly independent. Okay, and now I am given an arbitrary vector x, which consists of x1 and x2, two components. I want to reach to this point x. How I will reach it? So I will do c1 times 2, 1 plus c2 times 0, 3, and that should be equal to x1, x2. So now I got two unknowns that I'm trying to find, c1 and c2. And I have two equations, so it's fairly easy. I can do this. So this is 2 times c1 plus 0 times c2 equal to x1. And the next equation is c1 plus 3c2 equal to x2. Now here very clearly that my constant c1 is actually equal to x1. Okay, so I will pick my c1 as x1. And what about c2? I will pick, now that I know c1 is equal to x1, so I will put this x1 plus 3c2 equal to x2. So this gives me c2 will be equal to x2 minus x1 divided by 3. So now here it is. This is the one that I'm looking for. So here you can see very clearly that I can have c1 and c2. So given any arbitrary two-dimensional vector, then it is reachable by these two A and B. So all vectors in R square reachable by A and B. So they all are reachable. That's very important. We can access them by an appropriate linear combination, by an appropriate choice of C1 and C2. We can reach there. In other words, if I really wanted to depict it, this fact of reachable thing, I can say that I can reach here, I can reach here, I can reach here, I can reach here, I can reach this side, I can reach here, I can reach there, I can access this point, I can access this, I can access this, I can access. So all of this R square can be made provided that my two vectors, these two vectors A and B, are linearly independent. Okay, so if I got linearly independent two vectors, that's very important. If I got linearly independent two vectors, then I can make the whole R square. Now let us say you got three vectors, A, B, and C. Then one thing is for sure that C1 will be a linear combination of K1 times A1 plus K2 times B. So we cannot claim that C is linearly independent. The reason is because now C can be made. So if you have three vectors and you want to make R square, then definitely one of them is redundant. One of them is redundant. You don't need them. Redundant. So one is extra, I can say. The third one is not adding any information. You don't need it at all. And this is how. So what we are saying is that the span of AB is R square. Okay. And when we say span of AB, we mean is a linear combination. So let me write down the span in a formal way. So let's see. Here is the span of AB. Okay, so here I'm doing so the span of AB is basically we can say span of AB is actually a linear combination C1A plus C2B for all choices of C1 and C2, or we can say for all combinations of C1 and C2. And this should be arbitrarily equal to this R square. Okay, so this is the span. So now what is the basis? So if you can span the whole R square with linearly independent vectors, then these linearly independent vectors will become basis. So here is basis A, comma B. So basis consists of those vectors which are independent. Now here is the difference. Span, for example, I can span the same space. Let's say for the sake of argument, I can say one thing here is that let's say my A is 2, 1, okay, and my B is as I shown 0, 3, and my C could be the addition of these. So I can say this is 2 and 4. Now I can span. So if I do span of A, comma B, comma C, I will also do the same spanning. I will be doing spanning R square. But since C is a linear combination of A, B, I don't need it to span R square. So R square can be spanned only by A, B. However, when I do span, these three are spanning the same space. But for basis, I will pick from the spanning set only those vectors which are essential. And the vectors which are essential are basically linearly independent vectors. So I will pick A and B because these two vectors are linearly independent. The moment I put C in my basis, this is become kind of redundant and extra. I don't need it. So in the basis, we only put the vectors which are linearly independent and are essential to fill the whole space. So I will say, so the number of vectors in my basis set is known as dimensions. So this dimension is 2 here because the number of linearly independent vectors in the basis, the count is 2. Now there is one last thing that I would like to go over, and for this I will just take just a bit of cleaning work here, and which is about standard basis. So for R square, we can pick any 2 vectors which are linearly independent, then they will constitute the basis, any 2 vectors. However, most of the time, we basically go for something which we call standard basis. So what is a standard basis? In other texts, especially in the electrical engineering, we usually use I and j. So for R square space, okay, the standard basis is I, which we represent as 1 0, and j, which we represent as 0 1. These are called standard bases. One attractive thing about the standard bases are that these two are linearly independent, as you can see very clearly, because 1 0 1 cannot be produced from 0, and obviously this one cannot be produced from this 0. So these are linearly independent. But the other good thing about them is that I is perpendicular or orthogonal to j. Okay, there is an angle of 90 between them. So if I graph them, this is my I, okay, and this is my j. So there is an angle of 90 between them. However, these two are legitimate bases. So my basis for R square has 2 conditions. They should be 2 and they in count, and they should be linearly independent. So I and j are the basis for R square. These I and j are basis because they are 2, and but they have some additional property which is orthogonality. That's why we call them standard basis. So based on linear combination of I and j, it does span the whole space. So for example, if I want to reach to a point here, then this will be 3i and 2j. So this is 3i plus 2j. Okay. And also, if I want to reach to this point, then this one is 2i plus 3j. So I can reach to any point in this Cartesian plane, which I call R square space, using this I and j. And these are, so keep in mind that bases are not unique. So here I can claim that the third fact is that basis is not unique. The only condition on the basis is that it should be same as the dimension. So if you have R cube dimension, then you should have 3 independent vectors. If you have R4, then you need 4 independent vectors. But which basis is the more convenient one? It basically is based on the application. So there are certain applications. For example, if you are going into image compression, then the best bases are those wavelet bases, okay, are discrete cosine bases. But anyway, so but you can pick Fourier bases. So why in some application Fourier bases are better, and some the wavelet bases, and some the discrete cosine bases? This is based on the application in which you are using them, okay. So with that, I will come to the end of the lecture. If you have any question on this one, please, you can share with me, and you can put your comments on the YouTube video. Okay, thank you very much, and we'll see you next time.